Good morning. Uh, Welcome to the class today. So today is the last lecture for this course. Can you confirm me if you can hear me? So as you remember, we started this topic, concrete formwork design. So in the concrete formwork design, we earlier have already two lectures which were on the formwork design for the beams and slabs, and then the formwork design for the walls and columns. So today we will have the design of the lateral bracing. So these lateral bracings are the external supports needed for the formwork. So the formwork itself is strong enough that we can design, but externally, if the supports should also have to be strong. So for this purpose, we have here two examples. So we will briefly look at these two examples, and then with that, we will try to understand it. So first example is example number 3. So this example is for a wall formwork. So here you can see that there is this formwork for the wall. So you can see that internally there is a concrete wall, okay? And that concrete wall has been supported with the wall formwork, which consists of the sheathing and then the support beams, rails, etc. And then externally there is this inclined bracing. So in this example, we will be looking at the design of this inclined bracing. In the previous example, example number 2, we have already looked at the design of the sheathing and then these two cross beams which provide the support for the wall formwork sheathing, and then these lateral ties. So this external bracing design is to be considered over here. So example 3, determine the maximum spacing of a nominal 2 by 4 inch lateral braces for the wall form of example 2. So this example is related with the data, some of the data from example number 2. In example number 2, we looked at the wall with the height of about 2.44 meter. Okay, so the same wall we are considering over here. And then this wall is to be supported by 2 by 4 inch lateral brace. And this lateral brace is supported on the ground, and then on the wall it is to be supported. So as shown in this figure 4, assume that local code wind requirements are less stringent than table number 3. So which means that we will be using the requirements of table number 3. Okay. So table number 3 we looked at in our first lecture of this topic on concrete formwork. which provides us the allowable loads, allowable lateral loads. Okay, some of the values. So we will use table 3 because table 3 is more stringent than the local code wind requirements. So we may use table number 3. The allowable stress values for the braces are as follows. So the compressive stress in the brace is 45861, and the tensile stress is 4999, and the modulus of elasticity is 9.7 into 10 to the power 6 kilopascal. So these are the values which we will use over here. Okay, so in this example, so what we have to determine the maximum spacing. So first of all, we will determine the design lateral load per unit length of the form. So for example, if this is the formwork over here, perpendicular to this plane of paper as it is shown on this screen, perpendicular to the plane of this screen, per meter length, we will consider the force. So this force is 1.46 kilonewton, and this force is from table number 3. So for this we have to consider table number 3. So table number 3 is many pages over here, and that table number 3 provides us the value. So let's look at this table number 3. It should be here. Yeah. This is table number 3. So table number 3, what does it show? Recommended minimum lateral design load for wall forms. Lateral design load. So it says that if the wall height is less than 2.4 meter, then this is the design load. However, if the wall height is more than 2.4 meter but less than 6.7 meter, so then the design load will be 100. But it should be at least H by WF by 2. So it should not be less than 1.46. Okay. Or if this value H into WF by 2 is less than 1.46, we will take 1.46. If H into WF by 2 is greater than 1.46, then we will take H into WF by 2. So we will take the higher of the two values. Okay. However, it has already been said that the values given by table 3 are more stringent than the local wind force value. So WF is the wind force. Okay, WF is the wind force prescribed by the local code. So which we can take as like 0.72 over here. However, in this case, in the statement of the problem is said there, the values given by this table are more stringent. So therefore, we don't actually need to calculate H by WF by 2. So we will take anyway this 1.46 value over here. So that's why this value of 1.46 was taken. So it is here 1.46 kilonewton per meter. So this value we got from table number 3. Next, we will calculate the length of the strut. Okay, so the length of this lateral bracing, we call it as a strut. So the length of this lateral bracing will be, because we know it's horizontal distance from the formwork, and we also know its vertical distance from the formwork. So by the Pythagoras theorem, we can find its length. So it will be 1.83 square plus 1.53 square, and then take the square root of that. So we will get it as 2.38 meter. So we need the length Okay, we have the length. And this length we will use to find the axial concentrated load on the strut produced by a unit length of form may now be determined from the equation number 1. So equation number 11 over here. So this equation we can use. So this equation is simply the ratio of the dimensions of the wall and the respective dimensions of the strut. So for example, over here is H is the lateral force, which we already determined to be 1.46 kilonewton per meter. Okay. Whereas H is the height of the wall, H is the height of the wall or height of the form in this case, height of the wall or height of the form. L is the length of the strut, that means this length. So we will multiply this height with this length, and then we will divide by the horizontal, vertical and horizontal dimensions of the strut, H prime into L prime. So this is the formula. H prime is the height of the top of the strut, that is from here to here with this value, and then L prime is this value from here to here horizontal. So here we can see that P prime. So P prime is what? P prime is the strut load per foot of the form. That is, it is not the actual load in the strut. It is the per foot of the form. Okay. So as a proportion of the total load of the form in the form. Okay. So per foot of this length. So that's why its value will be in kilonewton per meter. So we take 1.46 per, which is the design load, design horizontal load on the formwork, multiplied by 2.44 meter, which is the height of the formwork, multiplied by 2.38 meter, which is the length of the strut, and divided by the vertical height of the strut multiplied by the horizontal height of the strut. So calculate this value. So we will get 3.03 kilonewton per meter. So this 3.03 kilonewton per meter is the proportion of the force in the strut, okay, per meter length of the form. Okay. That means it is the per meter, it is the force in the strut, force in the strut per meter length of the form. So this we can use. Actually, what we need is the total force in the strut. Okay, so that we can determine, of course, now. But for this, we will need to perform some of the checks. Okay, 3.03 kilonewton per meter. So where we will find that whether this force is more than the allowable values or not. So for this, we determine the allowable compressive stress, allowable compressive stress for each strut using equation 10. Okay, equation 10. The equation, what is the equation 10? 11 here. And somewhere there will be equation 10. Yeah, this is the equation 10. Okay. So equation 10 is this. So what is the equation 10? Fc prime is equal to 0.3 E divided by L over D square is less than or equal to F over Fc. Okay, so this equation 10 is for the concentrated loads on a column members. Okay, in column members, we will take this L over D ratio. Okay, so what are these values? FC is the allowable unit stress in compression parallel to the grain. Okay? And FC prime is the allowable unit stress in compression parallel to the grain, which is adjusted for the L over D ratio. Okay, so I think if you may have learned the theory of short columns and long columns, in that theory you may have come across this ratio, which is sometimes called as the aspect ratio, or which is in which we will take the length of the column and then divide the length of the column with the minimum lateral dimension. Okay, so L over D ratio. So based on this L over D ratio, the stresses in the column are adjusted so that those stresses are not greater than certain limits, which in this case is FC. So we will determine the FC prime. This FC prime should be less than FC. Okay, so FC prime is the allowable unit stress in compression parallel to the grain adjusted for the L over D ratio. So where E is the modulus of elasticity and L over D is the ratio of the member length to the least dimension. Okay, so now we go back to here and then we determine first the L over D ratio for this strut. So L over D ratio for this strut that is this member, L over D ratio is L is the length that we already determined, 2.38 meter, and then we convert it into millimeters, so therefore we multiply it with 1000, okay, and divided by its least lateral dimension, which is 38.1 millimeter. So why is it 38.1 millimeter? Oh, it is because we are using a section 2 by 4 inch nominal section, which is 50 by 100 millimeters. So it's 50 is the nominal dimension. Its actual dimension is 38 millimeters. For a 50 millimeter, the actual dimension is 38 millimeters. So that we can see from the tables. These tables. Yeah. So it is 2 by 4 inch. Okay. And 2 by 4 inch means 50 by 200 millimeter in millimeter dimension. But its actual sizes are 38 by 89 millimeter. Okay. So the least out of 38 and 89, the least dimension is 38 millimeters. So therefore, we will take 38 millimeters. So I go back to over here, 38 millimeter or 38.1 millimeter. So in this case, we calculate it and it is 62.5. 62.5 L over D dimension. So this L over D ratio for a short column should be less than 50. So I think from the theory of the column, so we should understand that we should design this strut as a short column. Okay, so for this short column, the L over D ratio should be less than 50. So, but here you can see that it is 62.5. It is greater than 50. So we should make it less than 50. So in this case, to make it less than 50, since the L over D ratio exceeds 50, each truss must be provided lateral bracing to reduce its unsupported length. So it means that this strut is actually quite long, okay, because its L over D ratio is greater than 50. It's quite long. So therefore, we should provide a lateral support to these struts. So that means there will be one strut over here, and at some distance perpendicular to this plane of this screen, there will be another strut over here. So those two struts will be joined with the lateral support as well. Okay. So there will be one strut, there will be another strut, and then there will be a lateral support as well. So therefore, it will be appropriate that we can provide that lateral support at half the length of this strut. So this means that its length will, for the calculation purposes, it will reduce from 2.38 meter to half of its length. So it will be 1.19 meter in this case. So therefore, each strut must be provided lateral bracing to reduce its unsupported length. So try a single lateral support located at the mid point of each strut. So reducing L to about 1.19 meter. Okay, so after we have provided this support, then we will check the FC prime. Okay, FC prime based on the formula which I just illustrated over here. FC prime formula from equation number 10 I just showed before. So it was 0.3 E, 0.3 into E, the value of E is given as 9.7, okay, and then into 10 to the power 6 divided by L over D ratio. So, but L over L is, we are using at half of this length, 1190, and D is this one. So now it is to be 2.97 kilopascal. Okay, 2.97 kilopascal. So this 2.97 kilopascal is fine. This value. It is less than FC. It is less than FT. Okay, this is okay. So this means that this 2.97 kilopascal value is the controlling value. It is the controlling value over here. So this FC prime this is FC prime is less than FT is less than FC. So this FC prime governs. Okay, so this actually should be read as FC prime, but it looks like written something else, but it should be FC prime. So the maximum allowable compressive force per strut is then as follows. So this is in the pound unit, so we can convert it into the units. So in this case, that will be the stress. So this value is 2.97 or it is 2.967. So 2.97 is approximate terms, it is 2.967. Okay, and because this is the allowable force, this is the allowable stress. This is the allowable stress in the stress in the strut. So the allowable stress in this strut is 2.967. So we will multiply by its actual area, which is 38 by 89 millimeter. And then to convert the units, we will divide it by 10 to the power 6. So in this case, we will get a force of 10.03 kilonewton. 10.03 kilonewton. So this value then tells us the force of 10.03 kilonewton can be applied in one strut. But we know that the force per unit length of the formwork is 3.03 kilonewton per meter. So if this total force have to be withstood into this allowable force in this strut, so then we will divide this 10.03 kilonewton by 3.03 kilonewton per meter. So which will give us a horizontal distance of 3.31 meter. So this will mean that this is our required answer. So this means that we will provide this lateral bracing at a distance of 3.31 meter. At a distance of 3.31 meter. That is, there will be one bracing, another bracing will be at 3.31 meter. But remember that we will also have to provide the lateral support to these bracings at about half the at the midpoint of these supports. So keep in mind that the design is based on providing lateral support to each strut at midpoint of its length. So in this way, we determined that these lateral supports can be provided at 3.31 meter. So how this was determined? So first we determined the force per unit length which is being applied by this formwork. And then we determine the allowable force in the strut. And then we divided the allowable force with the force per unit length, which gave us the horizontal spacing between these stress, between these struts or the lateral bracings. And remember that a lateral support for these struts is also to be provided. We did not actually provide the dimensions for the lateral support, but that can be any lateral support, any suitable lateral support, preferably the same dimension as these struts. So in this way, then the lateral braces for the walls and column forms can be designed. Okay, so in this, do you have any questions about this example? Okay, so with this example number 3 is completed. Now we can look at example number 4. Example number 4 is about the beam, lateral braces for the slab forms. Okay, lateral braces for the slab forms. So we may need to provide also the lateral braces for the slab forms as well. For two situations. So for elevated floor or roof slab forms, lateral bracing may consist of cross braces between the shores. So that means, remember that the last element for the slab form was the shore, but we may need to provide the lateral braces between the shores as well. Or we need to provide the inclined bracing along the outside edge of the form, similar to that used for the form works. So the following examples illustrate the method of determining the design lateral load for the slab forms. So just like for this column design, if we can determine the design lateral load, we can design the lateral bracing. So similarly, if we can determine the lateral load for the slab forms, we can also design the lateral bracing. So in this case, the example determines the design lateral load. Okay, so in this case. So what is this example? Example number 4, determine the design lateral force for the slab form, 152 millimeter thick and 6.1 meter wide and 30.5 meter long as shown. So this is 6.1 meter wide slab and 30.5 meter long slab is there. And then there will be horizontal forces. So one horizontal force will be in this direction and the other horizontal force in this direction. That means one horizontal force will be acting on the smaller side, the other horizontal force will be acting on the larger side. So we call them as H20 and H100 respectively. So we need to determine these horizontal forces in these examples. Okay, so in this case, the dimensions are given and it is shown in figure number 5. So the slab is to be poured in one pour. That means we are assuming that we will be pouring the slab in one go. Okay, and assume concrete density is 2403 kilogram per cubic meter, which is the normal concrete density, and the formwork is about 0.72 kilopascal. Okay, so in this example, first of all, we will calculate the dead load. Okay, so we will calculate the dead load. So the dead load we will calculate over here, 0.152 times 1. 0.152 is the thickness of the slab. 1 meter, we will take the 1 meter width of the slab. And then the weight of the slab, density of the slab is this 2403, and then multiplied by 9.8. This is to convert the kilogram into the Newton units. And then this 1000 is for converting newtons into kilonewtons. Okay, and then divided, then add it with, add to that is the dead load. That is the weight of the formwork. So this is the dead load, 4.3 kilopascal. 4.3 kilopascal. So from this dead load, there is a formula. H is equal to 0.02 times the dead load multiplied by the width of the slab. Okay, width of this. So this formula will be used to find the horizontal force. Okay, so this formula we can use for the H20 direction, that is the smaller direction, or this formula we can also use for the H100 direction, that is the larger direction. So in the H20 direction, so that means for the 6.1 meter face, the width of the slab is 30.5 meter. That is width of the slab. WS is the width of the slab. So that means if we take this direction, so the width of the slab we take is 30.5 meters. So the value of H according to this formula will be 0.02 multiplied by the dead load multiplied by the width of the slab, 30.5 meters. So we will take it as 2.62 kilonewton per meter in this direction. And then for the other direction, it will be 0.02 into 4.3. I think it should be 4.3 as well. 4.3 and 4.29 is the same. And multiplied by the 6.1 meter, which is in this direction. So this is 0.52 kilonewton per meter. However, this value, according to the codes, and I think it has been described before as well, it should not be less than 1.46 kilonewton per meter. According to the values in table number 3, this value should not be less than 1.46 kilonewton per meter. So in the H20 direction, 2.62 kilonewton per meter is fine. In the H100 direction, it should be less, should not be less than 1.46 kilonewton per meter. So based on these two values, 2.62 and 1.46, so we can then design the horizontal bracing according to the methods which were described before. Okay, so in this case, we just determined the lateral horizontal. We determined the design lateral forces on this beam on this slab forms. Okay. So this is only mainly the use of this formula 0.02 into DL into WS. That formula was used. Okay, so with this, we have covered all the 4 examples and this topic has been covered. Well, later on, I will share with you some of the practice problems with solutions of this topic. And then we will cover this topic in one of the questions in the exam as well. So that's all for this topic. And with this, all the contents of this course have been completed. And then maybe you can get ready for the exam. So, do you want to ask any question? Yes, this is the last lecture. I will not have a lecture on Thursday. So do you have any questions? So I already announced that we will have the exam, and then the topics of the exams are, I have already announced. Those are the topics which we covered after the midterm exam.
Okay, thank you.
Or later on, as I said, that this is the last lecture, or if maybe on Thursday you may have some questions, so maybe we can have about half an hour session on Thursday as well. Okay, so that will be a question and answer session. So maybe I think it will be better to have one more on Thursday, so you can ask any questions. Okay, so maybe we will meet on Thursday, maybe for half an hour, and then I will give you an opportunity to ask. Or maybe in that time you can review your topics.
Okay, thank you.
Just a bit. Usually you upload practice problems for midterm exam. Will you upload that kind of material for final exam?
Yeah, I have already uploaded practice problems for all these topics. So those practice problems which I have uploaded will serve as your practice for midterm exam.
So all topics covered in final exam will be after midterm. Yes, it's assignment.
Yeah, as you see, my
problems.
email. I specifically mentioned those topics. From topic number 6 to topic number 10. I mentioned the topics along with their names, so those topics will be covered. Did you see my email?
Yes, thank you, Professor.
Yeah. So to make everything clear, I sent it on the email. Okay, so that nobody has any confusion. Okay. So it seems that I think only very few of you have attended today, and then you don't have any questions. So okay, then I will maybe we can stop at this time, and then I shall see you for half an hour on Thursday. Maybe I will announce on also, so that if you have, and if any one of you have any questions, then you can ask questions on Thursday. All right then. Thank you. Bye-bye.
Bye.
Bye. Bye.
Bye.